Couple ways to tell if we have a function versus if we do not have a function. Once we get through that, we'll talk about the specifics of things that are functions, like we just reviewed with Blooket, proportional, non-proportional, linear, non-linear. So we know that it is a function. Let's say we've got ordered pairs, right? If we've got 2, 3, 3, 4, 4, 5. These 3 points do represent a function because we have no repeating input. Again, input being our x values. We have no repeating inputs. 2, 3, and 4 are all unique. That means we do, in fact, have a function. Now, we don't know if it's going to be a straight line or a parabola or anything in between, but we do know that it is a function when there's no repeating input. Conversely, it is not a function if we have 2, 3, 2, 4, 4, 5, something like that. Because we do have those repeating inputs with different outputs, that would not be a function. So this has a repeating input, different output. Like we said when we first learned this, if you put cookie dough in the oven and get out cookies, the next time you put that same cookie dough in the oven, you're not going to get out brownies. That's impossible. It would not happen. If it does, your oven is not functioning properly. Okay? So repeating inputs like that, not a function. And it doesn't have to be all the inputs repeating, right? 4 is unique. But as soon as we have 2 of the same x coordinates, right away, it is not a function. All right? Does any of this sound familiar? A little bit? Okay. Now we can also see this in what's called a mapping diagram. Right? If we see something like this, this is called a mapping diagram. It's just a kind of a different way to represent this same thing with these points, where the input is traced over to a single output with an arrow. So if we wanted to convert this mapping diagram into coordinates like this, we could say 1, 5, 2, 4, and 3, 6. We just follow the arrows. So because there's no repeating inputs, right? 1 has a single output, 2 has a single unique output, and 3 has a single unique output, this is a function. Each input has exactly 1 output. Let's write that. Each input has exactly 1 unique output. We can even write in and out up on the top of our mapping diagram like that. Now, we know that our mapping diagram is not going to be a function if we see something like this. If we've got 1, 2, 3, 4, 5. Let's say that my input of 1 gives me an output of 3, but my input of 2 gives me an output of 4 and an output of 5. Just like we saw up here, right? 2 to 3 and 2 to 4. Here we've got 2 to 4 and 2 to 5. We cannot have that. So we could say input of 2 has 2 different outputs This is not a function. It's a bad T over there. There we go. All right. So that's how we can tell. That's really the only ways we need to know how to tell whether something is a function or is not a function. So now let's focus on what is a function. When we have a function, we can describe that function with these four terms. And it's exactly what we just saw on that Blooket activity. Let's start out with linear and proportional. If we have a function that is linear and proportional, we're going to have no exponent and a b value of 0. No exponent, b value of 0. On a graph, it would look something like that, right? Through the origin, straight line. If we had an equation, it would look something like y is equal to 1/2 x. There's no exponent on my variable. There's no b value being added onto the end. That is linear and proportional. All right. We could also have linear and non-proportional. If we have a function that's linear and non-proportional, there's still not going to be an exponent in our equation, but our b will not be equal to 0. B will, that's a large 0, but that's okay. B will not be equal to 0. So we'd have a line that looks something like that. Again, where we do not cross through the origin. And our equation would be something like y is equal to 2x plus 3. Right? I've got a b value being added on the end, but I still don't have an exponent in my equation. Yeah, Ross. Sure. Last but not least, we have nonlinear and non proportional. This one has an exponent. Sorry, I'm going to move down. Nonlinear and non-proportional. This one has an exponent. And B can be anything. This is the important distinction that we need to make. Even if our B value is 0, if it's nonlinear, automatically it's non-proportional. This will look something like that. Right? We call that shape a parabola. U-shaped graph, not a straight line, obviously. And our equation would look something like y is equal to x squared, or y is equal to x squared minus 3. So this is what I mean by B can be anything. B can be a number, like 1, 2, or negative 3. But B can also be 0, like in this first equation. Even if my B is 0, this parabola goes through the origin. It is still non-proportional, because for a line to be proportional, it has to be linear. I feel like a broken record. I feel like we've been saying this a lot, so hopefully it's stuck in your brain by now. If we have a proportional function, it is a straight line through the origin. Even if it goes through the origin, if it's not a straight line also, it is non-proportional. So notice how the three options are linear proportional, linear non-proportional, non-linear, and non-proportional. What option is not up there? What combination of those terms is not up there? Anyone see it? What combination of terms is not an option? Yeah, Breeza. Bingo, exactly. Nonlinear proportional will never, ever, 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 ever be the case. It is impossible for something to be nonlinear and proportional. Great catch. All right. That 1,000% will be a test question. I wrote that question this morning, so make sure you keep that in mind. All right. Let's see. Let's talk about function tables real quick, and then we'll kick it off with F06. Let's say I've got a function table of, we got my x column, I've got y is equal to x squared plus 1 as my function. Got my y column. And x comma y. There's my solution. Oops. So let's say I've got some x values of -2, -1, 0, 1, and 2. Table doesn't have to be perfect. Don't need to use a ruler or anything. Just make it like that. Just like we saw in the warm-up, this is what we did. We're going to take out my x value, plug in each of these 5 inputs, and we'll get an output of y. So for the first one, we get y is equal to negative 2 squared plus 1. What is negative 2 times negative 2? Anybody know negative 2 times negative 2?
Negative 4.
Negative 4 is very, very close. Positive 4, right? Anytime we square a negative, we get a positive. And 4 plus 1 equals 5. So my solution here, negative 2, comma 5. If we take the next point, y is equal to negative 1 squared plus 1. Close. Negative 1 times negative 1. What would that be? Positive 1 plus 1 equals 2. My solution, input negative 1, output positive 2. Are we seeing what I'm doing here, or is there some confusion? Yeah, of course we've done this before. We're reviewing. This is even on the test, I think, that we took a couple weeks ago. Third input is 0. Y is equal to 0 squared plus 1. What's 0 squared? Just 0. Plus 1 gives me 1. So my solution is 0, comma 1. Second to last input is 1. Y is equal to 1 squared plus 1. What's 1 squared? Is that 2? No, it's 1. 1 times 1 is 1. And 1 plus 1 is 2. Bless you. This is where we're going to start to see a pattern in our outputs. We remember this pattern. It's not a linear pattern. It's not going to be the same change in y from point to point, but we will see something interesting happen when we have an exponent in our function. Last input is 2. Y is equal to 2 squared plus 2. What's 2 squared? 4. Perfect. Plus 1. That gives me 5. What do we notice about our outputs in this function table? Do we have 5 unique outputs? No, we've got repeating outputs, 5 and 5, 2 and 2. Is that okay? Yeah. Yes, it is. These are outputs. If you remember, we cannot have a repeating input. All the x coordinates here, or all the x values, are different. It's fine if they produce the same output. This is still a function. But when we have an exponent here, we should notice that my outputs are going to be mirrored along that 0. Right? So my output for 0 is unique. The 2 next to that are the same. The next 2 are the same. The next 2 will be the same, and so on. That's why we get that U shape on our graph. Kind of bends back up as we go through all those inputs. All right. Is there anything else we need? We did that yesterday. You guys can have fun with that. All right. Questions?